Now let's see two more concepts where we will derive formulas. Let's consider a complex number z1 in the polar form or in exponential form. So in exponential form we can write it down as r1 e raised to I theta 1. Similarly, let's consider one more complex number which is r2 e raised to I theta 2. Now we are gonna see what will be the result of multiplication and division of two complex numbers in polar form or in exponential form. So if I want to divide these two complex numbers, let's see what it will give me, and after multiplication what it will give me. So z1 into z2, here I am doing multiplication. So after multiplication we will get r1 r2, and here you can see I theta 1 and I theta 2 are in power of e. So we will use laws of indices over here. So using laws of indices, if base of two numbers is similar, then we can add their powers. So it will give me e raised to I theta 1 plus I theta 2, which ultimately will give me r1 r2 e raised to I theta 1 plus theta 2. So here you can see now r1 and r2 is our new modulus and theta 1 plus theta 2 is new argument. So argument of z1 into z2 is theta 1 plus theta 2 and modulus is r1 into r2. Similarly, if we will perform the division of these two complex numbers, that is z1 upon z2, it will give us r1 e raised to I theta 1 and r2 e raised to I theta 2. Now here you can see that r1 and r2 is real number, so we will divide it in general manner, that is r1 upon r2. But here e raised to I theta 1 and e raised to I theta 2 both are in the exponential form, and I theta 1 and I theta 2 is in power. So here again we will apply laws of indices. So according to laws of indices, this I theta 2 will go in the numerator and will become negative. So it will give me e raised to I theta 1 minus I theta 2. So we get r1 upon r2 into e raised to I common in bracket theta 1 minus theta 2. So in this case you can see that the modulus is r1 upon r2 and the new argument is theta 1 minus theta 2. Now same results we get when the given complex numbers are in polar form. So let's see one more example. So let's say z1 is equal to r1 cos theta 1 plus I sin theta 1. Now here you can see the number is given in polar form, and z2 is r2 cos of theta 2 plus I sin theta 2, again a complex number in polar form. So if I want to multiply this or divide this, what will get? So z1 into z2, this is my first operation, will give me, here you can see if we want to multiply two complex numbers, we need to use the rule of algebra, that is to multiply the second bracket with the first term and again the second bracket with the second term. So I will write it horizontally. So it will give me r1 cos theta 1 plus r1 sin theta 1 I into z2 is nothing but r2 cos theta 2 plus I r2 sin theta 2. So it will give me r1 cos theta 1 into second bracket is r1 r2 cos of theta 1 into cos of theta 2 plus I r1 r2 cos theta 1 sin of theta 2. I will again multiply the second bracket with the second term, that is I r1 sin theta 1. So it will give me plus I r1 r2 sin theta 1 cos theta 2 plus this term into this term will give me I square r1 r2 sin theta 1 into sin theta 2. Now you all know that I square is equal to minus 1 because I is equal to root of minus 1. So we will substitute I square as minus 1. So what we'll do is we will take all real parts together and all imaginary parts together. So this last term and this first term will become real and we will take it together. So it will give us r1 r2 cos theta 1 cos theta 2 minus, because of this I square, r1 r2 sin theta 1 sin theta 2. Similarly, this second and third term consist of imaginary term, that is I. So we will take these two terms together by taking I common. So it will give us plus I r1 r2 cos theta 1 sin theta 2 plus r1 r2 sin theta 1 cos theta 2. So we will get here r1 and r2 can come as a common. So I am taking common term outside. Inside bracket cos theta 1 cos theta 2 minus sin theta 1 sin theta 2 will remain. Similarly, in the second part, I r1 r2 outside, inside bracket cos theta 1 sin theta 2 plus sin theta 1 cos theta 2. Now we all know the formula, that is cos A into cos B minus sin A into sin B. It is always cos A plus B. So it will give us cos of theta 1 plus theta 2, because here A is theta 1 and B is theta 2. Similarly, sin A into cos B plus cos A into sin B will give us a formula sin A plus B. So here we will get sin of theta 1 plus theta 2. Now we can take r1 and r2 outside bracket, and inside bracket we will get cos of theta 1 plus theta 2 plus I sin theta 1 plus theta 2. So here you can see that we got r1 and r2 as modulus and theta 1 plus theta 2 as the argument, which we have got in the exponential form. It means whatever result that we are getting in the exponential form, same results we can get in the polar form. So using the same method, you can try the second formula by your own and you will get the same result. So here we have seen how to divide and multiply two complex numbers when they are given in polar or exponential form. Now using these concepts, we will see some more examples which will make your concepts clear. So before starting examples based on that concept, we will see one more formula which is based on the previous result. So here we will see how this result is derived. So the result is argument of z1 into z2 is equal to argument of z1 plus argument of z2. So to prove this result, we will need the result that we have proved in the previous slide. So in the previous slide, you must be remembering that we have proved z1 into z2 is equal to r1 r2 into cos of theta 1 plus theta 2 plus I sin theta 1 plus theta 2. So now we will use this result to prove this new result. Now to prove this new result, that is argument of z1 into z2 equal to argument of z1 plus argument of z2, let's consider two complex numbers. So one complex number is z1, that is nothing but r1 into cos of theta 1 plus I sin theta 1, and another complex number z2 as r2 cos of theta 2 plus I sin theta 2. So, this arg of z1 is nothing but r theta 1, and arg of z2, that is argument of z2, is nothing but theta 2. Now, to prove this result, we will start with the LHS. So, LHS is given as argument of z1 into z2. So, here argument of z1 into z2 as proved in the previous result is theta 1 plus theta 2. So, we can take it directly, theta 1 plus theta 2, and we all know that theta 1 is argument of z1 and theta 2 is argument of z2. So, ultimately it proves this new result. So, it is nothing but our RHS. So, you all have seen that to prove this result, I have used the previous result, which shows that argument of z1 into z2 is theta 1 plus theta 2. So, this is one more formula of complex number which will be useful in solving numericals. Similarly, we have one more formula which looks similar to this, that is argument of z1 upon z2. So, here the answer will be argument of z1 minus argument of z2. So, this is one more formula. So, these are the two new formulas which we will use to solve numericals.